Okay, we are going to start now. Okay, so the idea for this webinar is to compare the different battery technology according to the main parameters interesting the battery world. Be aware that we are going to deliver a large number of numbers. We are not going to comment all the numbers. The idea is just to comment the key points. And this document will be available after the webinar for you. You keep all the numbers with you and look for them when you will need them. So first of all, according to the main characteristics, so we can speak about first of all about voltage. The voltage of the battery is not the same according to technologies. For lead acid, it is 2 volts. It is 1.2 volts for nickel products, nickel cadmium and nickel metal hydride. And for lithium products, it varies from 2.4 to 3.6 volts. According to energy density, so energy density on volumetric energy, I guess that what is very important to keep in mind is that lithium ion is the more attractive technology for energy density, to have the smaller battery as possible. But you have different type of lithium ion, and for example, lithium iron phosphate or lithium titanate, the energy density is close to nickel metal hydride products. So it is very different to traditional lithium ion.
Now we will speak about the charge. The charge on the different technologies is different. In fact, you have two families. The first family that is mainly charged with constant current, nickel-based technology, for example, and one family is charged with CCCV, that means constant current and constant voltage. This is the main characteristic. In that case, the charge is done in 2 or 3 steps, but the first 2 steps are constant current first, up to a threshold, a voltage threshold defined depending on the technology. And then there is a constant voltage phase where the current will decrease during the charge. So what is important to note is that the end of charge is very different depending on the technology. And the advantage of lithium ion is to have a more rapid charge than other technologies, except for the power nickel metal hydride, where you can have a very fast charge. So this is really a main criteria, a main benefits for this technology. Another point to note in lithium ion too is that the charge is prohibited below 0 degrees. That means it's forbidden to charge when the battery is very low temperature. It's not a question of performance, it's just a question of safety. In fact, in that case, we can create some metallic dendrite inside and some metallic part, and so we can have a short circuit inside the cell. So this is why it is very, very clear from manufacturers and very strict rules to respect, not to charge below 0 degrees. Another main difference is that for nickel metal hydride, you can charge up to very high temperature. That means you can start the charge at 65 or 70 degrees. So it is the only technology where you can charge at such level.
According to the discharge curve, in fact, you have 2 families. One where the discharge curve is flat, and in this condition, it is not possible to use the voltage information to know the state of charge. And at the opposite, some technologies like lead acid or lithium ion, where the evolution of voltage is I would say, significant enough to be a way of knowing the state of charge. According to the end of discharge, voltage is not the same according to the different technologies, but it is also in relation with the voltage of charge. So you can see that there are different values. What is important to keep in mind is that according to power, lithium ion deliver a higher power compared to the other technologies. at the exception of the nickel metal hydride power, a technology which is designed and dedicated to power applications. For the temperature in discharge, there is no major, I would say, differences between technologies. Only point to keep in mind is that nickel cadmium has a particular and excellent behavior in power at very low temperature. This is the main reason why nickel cadmium is still used today.
Now, on some application, very often customers are looking for the state of charge of the product. So the state of charge can be calculated or evaluated by two ways. The first way is based on the voltage value during the discharge. This is mainly used when the current is quite low and stable. That means that the discharge curve can be used all along the discharge, and so we can have a correspondence between the voltage and the state of charge. This is the case for lithium-ion products and for lead-acid products. However, for the other technologies, the discharge curve, as you have seen before, is quite flat. And in that case, the voltage is not representative of the state of charge. So there is another way to calculate it by using a Coulomb meter. That means we will calculate, we will make the sum of what is entered as an ampere hour, what the capacity is charging the battery, and we can also calculate what is discharge. And doing this, we will evaluate the state of charge of the product. Coulomb meter can be used on the specific circuit board, but there is some I will say, drawbacks. The fact is that sometimes you have to recalibrate the value, so you have to make a full charge-discharge cycle to have it accurate. And especially when you have a very long storage, that means you have to recalibrate the battery pack just after the storage. So this is the main drawbacks, but this is something that you can plan, or you can enter it in your documentation for your users.
Considering the life duration of the battery, it is very important to keep in mind that two parameters influence the life duration, and I would say this is true for every battery technology. One is temperature, and the other one is the depth of discharge, meaning that the percentage of the available capacity that you are using during each cycle. So for the temperature, the higher temperature, the shorter is the life duration. And for the depth of discharge, the smaller is the depth of discharge, and the longer life duration you will have, and you will get more cycles. So this is the reason why that the comparison that we are presenting here is valid for a cycling of 100% of depth of discharge, and also it is at room temperature. So if you compare the performance level of the different battery technologies, you can see that, I would say, first of all, lead acid is the technology delivering the lower amount of cycles. Okay, after you have the traditional lithium ion with 300 to 800 cycles, then nickel cadmium, and after, I would say that you have three technologies delivering a very large number of cycles: nickel metal hydride dedicated to cycling, lithium iron phosphate, and titanate.
Another interesting comparison is the storage and the self-discharge of the technologies. First of all, for nickel and for lead acid, it is recommended to store the products, I will say, more charge, so with a higher charge than 30%, but the more charge is the better. For lithium ion, it's the opposite. In fact, it is recommended to charge them less than the half of charge, because if you have a full charge battery store, then you will have some capacity loss irreversible. So that means it's better to store them with a low state of charge. Then the duration for the storage is different because it's really linked to the self-discharge. For lead acid, nickel, you can see that the storage duration is recommended around 6 months. And then you will have to check and very often to recharge product to store them again. For lithium ion, you will see that the duration is around 1 year at room temperature, I would say around 20 degrees, the same as for titanite. Then, as you can see, the temperature has also an effect on the storage. If the temperature is increasing, the storage will be decreased in terms of duration. So that means you have to store very short term in a high temperature. The self-discharge, in fact, is quite varying from a technology to another. What is interesting to note is that for lithium iron phosphate, and lithium titanite, the self-discharge is the lower from the other technologies. So this is where you will have a very interesting storage conditions. That's why you can store them for 1 year or even more sometimes in the conditions of standard conditions. But don't forget, when you have some batteries, that sometimes you have electronic in the battery pack, and sometimes you have electronic in the device that can consume currents. And in that case, you have to take into account that those values are only valid for the cell. That means if you had electronics, you have to add your consumption.
Considering safety on recycling, first of all, safety, one very important point is that you have two families, or let's say three, flammable and non-flammable technologies. First of all the battery technologies using an aqueous electrolyte, so acid electrolyte or alkaline electrolyte, like lead acid, nickel cadmium, nickel metal hydride, those batteries are non-flammable because the electrolyte is aqueous. And so they have some very low or no constraints at all for transportation. After you have some flammable technology, all the lithium ion technologies are flammable. Traditional lithium ion is highly flammable because of its higher energy density. LFP and titanate, they are flammable also because the electrolyte is flammable, but the consequence during a fire is less, I would say, is less strong. The effect is, even if it is flammable, it is not as explosive as the traditional lithium ion. Considering recyclability for lead acid and nickel cadmium, we can say that the recycling process is simple and efficient. I would say well known because it is implemented during many years. For nickel metal hydride, also the process is well known and implemented since many years. But the difference compared to lead acid and nickel cadmium is that the recycling of nickel metal hydride is highly profitable because in nickel metal hydride you have a significant amount of nickel, cobalt, rare earth, and so the value of the waste is very interesting. You have approximately 40% of nickel in weight in a nickel metal hydride battery. For traditional lithium ion, the process is not simple. Also, it is not profitable because there is not a lot of high-value metals inside or high-value components. And for lithium iron phosphate and titanate, it is difficult process, not easy to manage, and not efficient. But I would say that for all lithium ion technologies, the process is not really yet established, and so we can imagine that in the future some improvements will be made.
Just a small comment about lithium-ion technologies. As you have seen before, we have separated three big families of lithium products: lithium, lithium iron phosphate, and lithium titanate. In fact, there is much more different technologies in lithium-ion. And so we have lithium cobalt, we have lithium manganese cobalt, lithium nickel aluminum. So there is a large range of technologies. All of them are not equivalent, and some of them are more focused on power ability, some are more focused on energy, or some on safety or cycle life. What is important to note is that depending on the power and on the safety cycle life, the best compromise is NMC technology as a lithium, because you will have quite a good performance on all items. But the safest of all of them is really the iron phosphate, where the safety is really key, because this technology is more stable than the other. So you do not have the same aggressivity of the cell. Another point regarding the energy density is that you can see that NCA are very good for such criteria. So talking about lithium in terms of general approach is really interesting to have the I would say the behavior for charging, discharging, and so on. But then when you want to choose really the good technology regarding your application, then you have to dig further and to ask for one technology, or to ask for counsel, to have advice to choose the good one.
What I used to say when I meet some customers is that there is not a battery technology which is better compared to the other one. In fact, in the battery world, there are many battery technologies, but each one has some benefits and drawbacks. And so the game is to well know the need to be able to propose the relevant battery technology. If we make a comparison, for example, lead acid is very interesting because it is the cheapest battery technology, easy to find with standard sizes and products. But at the opposite, in terms of performances, it is not very high level performances. You have a low cycling. You need to oversize the battery if you want to get some power. The temperature range is limited. So I would say even if today lead acid satisfy a significant amount of applications, because this technology is used a lot in terms of quantity, but in terms of performances, it is the most poor battery technology. It is mainly used today in forklift, in UPS, on backup applications, a lot of backup applications, because the battery does not cycle and it is not used strongly. For nickel cadmium, the main benefits of nickel cadmium, it is the power at very low temperature, -30, -40. The drawbacks is that the energy density is relatively low, and the main application is backup, and also the main application is the start of engines in very cold countries like North America or North Europe. Nickel metal hydride, the main benefit is cycling, the large number of cycles, the large temperature range, and the long life duration. The drawbacks is the self-discharge, and this technology is mainly used today in stationary outdoor applications or solar applications in hot areas. According to nickel metal hydride high power, the main benefit is the very fast charge. You can charge in less than 3 minutes. And so in many applications, you can downsize the battery size using this technology. The drawbacks is that the energy density is not so high, and it is mainly used today in HGV, robots, and peak shaving applications. Lithium ion, the main benefit is it is very light and compact, so you have a smaller battery. Also, it delivers high power. The main drawbacks is that you cannot charge below 0 degree, and it is mainly today used in robotics, professional electronic, and also a lot in indoor application because of the limitation of low temperature. Lithium iron phosphate, the main benefits is a long life duration. It is compatible with lead acid chargers, and the drawbacks is that you cannot charge below 0, and also the performance at low temperature is not so good. It is mainly used today in medical application or solar applications in temperate areas. According to the titanate, lithium titanate, the main benefit is a very long life duration, the longest in the world of battery. You can charge below 0 compared to the other lithium-ion technologies, and it delivers a high power. The main drawbacks is the cost of this technology, and it is mainly used today in AGV and in stationary application. So we made a summary of all the parameters we have described today. We are not going to come back on the numbers, but it is just for you, for you can use it when you need it. So it's a full synthesis.
And then just to finish our presentation, we just want to define or to show you what are the technologies on the road today for tomorrow. And so we have different technologies that today are already used, such as a lithium metal polymer. So technology that is using a lithium metal product, but with that must be heated to be functional. So this is something running. Then there is some study about solid state. Solid state will be certainly the future with a higher energy density, up to 500 watt-hour per kilogram, and high cycling. This is what is targeted. And this technology, I say, will be perhaps mature around 2030, something like that, for production. We have also sodium ion. Sodium ion is a technology that is cheaper than lithium ion. And today they have a lower energy density, but the safest behavior. And so manufacturers are targeting long cycling, not yet reached, but on the way. And some products are already in prototype or pre-series phase. And this product, I think, could be available in mass production in 2020, 2022, something like that. Then we have lithium sulfur. Lithium sulfur is another type of product. And the voltage is quite different. It's a little lower than lithium ion. But the energy density should be higher than the lithium ion we have today. And the cycling too. The main drawbacks today is that the reaction is not yet completely managed. And so this technology is today in samples for small capacities, and it will be developed in the coming years to be more mature and more production phase. And then in the real future, we will say about 2050, 2060, something like that, there is some lithium hair products that are on the way, but it is mainly today research programs. And so they have some proof of concept that are already done. The fact is that with this technology, the target is to have very high power energy density. So we can reach, we hope, 2000 watt-hour per kilogram. But today it's really in research phase. And so those systems won't be ready before long term. And so this is an overview of what we can see in the future. So as you can see, the technologies are still moving, still going ahead. And so the products are not, I would say, the presentation of today won't be valid in 3 years, But I think it's a good exercise and a good overview of what we can propose, what we can have on the market.
So the presentation is finished now. As usual, we propose that you send some questions, but for sure we are going to receive a lot of questions, and we will not have to answer to all of them. So please, we invite you to send your questions to Iris or myself. You will find you know us, or you will find the email address at the end of the presentation. But you can start with some questions. We will ask to a few of them. So there is a question according to BMS, battery management system, according to battery technology. I would say that the battery management system is mainly in relation with the way of detecting the end of charge. So for nickel metal hydride, when you speak about BMS, the key point is the choice of the end of charge detection, plus the state of charge. So we use a coulometer. And for lithium ion?
For lithium ion, the BMS, in fact, is managing the safety first. So you have some parameters that have to be checked and controlled by your electronic circuit. And then your BMS can also manage the charge. So that means the value of the current, the value of the voltage. And this is mandatory to have a protection BMS inside the battery pack. Today, we focus the presentation only on the technologies, not on the way of managing the whole battery system. And perhaps it should be another webinar we can propose on such items. And so we will think about it.
The second question is according to titanate, and the question is why the titanate can charge below zero. Is it a lithium technology?
Yeah, lithium titanate is somewhere a lithium technologies, but with different anodes and cathodes. And so, in fact, there is some possibility to charge it at low temperature. And it has been defined and it has been characterized to be charged in a such way. So this is really linked to the technology used internally in the cell.
We have another question about titanate on low temperature, so I guess that Iris made the answer.
With titanate, if we work below 0 degrees, it's not a problem. It's something in the range of the specification. However, it is not the same for iron phosphate or for standard lithium. In iron phosphate or standard lithium, the electrochemistry inside makes some particles. And so in that case, it's not possible for safety reason to charge. It is not, as I said during the presentation, it is not a question of chargeability or a question of performance. If you charge a battery below 0, you can charge it. It's possible the battery will accept. But there is a safety risk associated too. And this is why it is forbidden.
The next question is according to nickel metal hydride. The question is that the electrolyte is water, so how can you charge below 0? In fact, the electrolyte is not water, it is aqueous, but it is not pure water. It is very concentrated alkaline solution. And so the frozen temperature is not 0, it is around minus 50 degrees C. And so you're right that the key point is the temperature where the electrolyte freeze. And so I would say down to minus 45, down to minus 50, we can use the battery because the electrolyte is not frozen. We
just had one last question during the webinar. Someone asking for a question about storage state of charge. Why using a lowest state of charge than 50% for lithium ion product? As I said, it's just because if you store it at a high level of state of charge, you will decrease the capacity and you will have a loss irreversible. So that means you won't have the full capacity of your battery after. This is only a question of performance.
Okay. We are going to stop now because we try at each webinar to spend maximum half an hour. And so thanks again for your participation. I hope that the information you got were of interest, were interesting. Remember that there is no stupid questions. And so if you want to ask additional questions, please contact Iris or myself.
We will send you an email tomorrow, the day after, using where you will find the presentation and the webinar recording, so you can use it for you and for your teams.
Thank you very much. Bye-bye.
Thank you. Bye-bye.